Hi, welcome to today's webinar. I'm Tony Gibbs, a data warehousing solution architect with Amazon Web Services. And today I'm going to be walking you guys through best practices with Amazon Redshift. So just to kind of cover the overview of what we're going to be covering, we're going to start out with the history and development of Redshift, kind of, where Redshift came from. After that, we're going to build up some concepts, some terminology, some Redshift-specific terminology, so you can understand the rest of the webinar and kind of, just build up that framework. We're then going to jump into some table design, ingestion, and ELT best practices. Then going to cover workload management and some of the best practices for configuring that, and then go into the node types and cluster sizing and kind of how best to size your Redshift cluster. And we'll wrap up with, just some additional resources for you, some links and things so you can move on to new things. And then with whatever time we have left over we'll do open Q&A. All right, getting started with the history and development of Redshift. Redshift really kind of starts out its life as Postgres. In fact, actually, if you connect to Redshift, you'll actually get back a Postgres connection string. And that's because Redshift was originally forked off of Postgres. We obviously changed it quite a bit. In fact, we actually made it a Columnar data storage engine. So all the data in Redshift is stored in a columnar format versus a row format like Postgres. We also made this system MPP, which is massive parallel processing. This is so that it allows Redshift to scale horizontally up to 2 petabytes of raw storage. We also added a lot of OLAP functionality as well. These are, query functions and such that you typically run in an analytics system, so things like approximate count distincts, for example. We then wrapped all of this up in the AWS ecosystem. So this is tight integration with things like EC2, KMS, so you can do full transparent data encryption, CloudWatch and SNS, so you can get alarms and all of that through, from your Amazon Redshift cluster. And that really, this whole combination of these changes and wrapping it up in AWS is really what makes Redshift what it is. We originally launched Redshift in February 2013, and since that time, we've been continuing to evolve the service. We typically release patches on a 2-week cadence. When you set up your Redshift cluster, or you can even change this at any time, you set a 30-minute maintenance window. And in that 30-minute maintenance window, that's when we roll out patches. So these are things like security patches, maybe for the operating system, as well as enhancements. So all of that is taken care of for you. We take care of it. It's a fully managed service. So moving into some of the concepts, I'm going to start out with just kind of an overview of the architecture here. So at the very top here, the green box there, SQL clients and BI tools. That's what you're using to connect to Redshift. We supply JDBC and ODBC drivers. If you're using something else or want to connect, say, from Python or R or Ruby, for example, you can actually also use any of the Postgres compatible drivers to connect to Redshift. Your connection goes through to that top blue box there, what we call the leader node, and that acts as your SQL endpoint. It stores metadata about the cluster, and it also coordinates all of the query processing through to the compute nodes, which are those blue boxes across underneath the leader node. The compute nodes hold all your data and also do all of the actual query processing. So we'll talk about that in much more depth. Those compute nodes, one important thing to realize is that they execute all of the queries completely in parallel, and they also talk to our other services such as S3 also in parallel. So the idea here is when you're, say, loading data into a Redshift cluster, say from S3, all of that loading happens completely in parallel. And this whole parallel MPP is kind of known also as a share nothing architecture. About a year and a half ago, we released an extension to Redshift that we call Amazon Redshift Spectrum. The Spectrum layer lays in between the compute nodes and S3. Typically, it's used for querying, say, Parquet files, ORC files, JSON, CSV, for example, directly from your Redshift cluster. So if you have data in S3 in one of our supported formats, you can execute Redshift SQL against those files in S3. You can even join the files, the data in S3 to the data that's in your local Redshift cluster. Another use case, which we'll cover in our ingestion and loading section, is loading data. Some customers even load data through Amazon Redshift directly into their cluster, for example, using an insert statement with a select from your external tables. So the first piece of terminology I'm going to introduce you to is Columnar. I kind of mentioned it earlier, and what this really is this is how the data is laid out on the disk in Amazon Redshift. So in a typical database, data is stored by row. So you typically would store the data row by row. However, in Redshift, we store it by column instead. And the reason we do this is because analytics queries typically only read a subset of the columns, and you're reading many rows. So for example, you might want to, say, do a sum of a couple million rows. By storing that data by column, it's actually much more efficient and saves I/O. So just to kind of illustrate this and give you an example of how this works, suppose we have this deep dive table up here on the top left, and just a handful of rows in it, we'll say. And we want to select, we're going to write a query against it, and the select statement here is select the minimum date from this deep dive table. Now in a row-based database, what would end up happening is you'd end up reading the entire table off disk to find that minimum date, assuming there's no indexes or anything like that to optimize. Now in a columnar system like Redshift, what would end up happening is we would only need to read the data for that date column off disk. The next piece of terminology to introduce you to is compression. Sometimes we'll use this term interchangeably with encoding. So I'm going to kind of, if you hear me kind of switch back and forth between those, in Redshift they kind of mean the same thing. Now what compression does is it's how we essentially store, we typically compress data in Redshift or want to compress it on disk. And this does two main things. First, it allows you to store up to 4 times more data in your cluster than you would if there was no compression. This greatly reduces the cost for you, so you'll want to definitely compress to reduce cost. The second benefit is that it actually also increases performance of your queries. And that's because it reduces the amount of I/O that Redshift needs to do. Typically in most clusters, I/O is the bottleneck, not CPU. So you'll want to make sure you definitely have compression. Now, Redshift does do the best it can to make sure that there is compression on tables. In fact, the first time you load data into an empty table with our copy statement, it will add compression to that table if you didn't add any. There's also a utility built into Redshift that we call Analyze Compression, and you can run that at any time against a table. You just type in Analyze space compression in the name of the table. And what Redshift will do in that case is it'll pick up data out of the table, a large sample set, and it'll compress it with every compression type that we have, and it'll return back the result that was the smallest, or what would result in the smallest table. Just to illustrate with an example of kind of how compression works here, or how you'd manually apply compression to a table. This is the same table as I had in the previous example. What we would do is we would change the DDL. You can see I've highlighted the text in red there. And that would be, how you would basically specify it. Now, one thing I'm going to call out is that each column can have its own compression type. So that first one, for example, is Z standard. The date there is run length. And that means that each column has its own compression and can grow and shrink independently from the other columns. So some of the best practices for compression, obviously, there's not really any downside in most cases to compressing a table. So you pretty much always want to apply compression to a table. And if you're ever unsure of what compression to apply, just use the Analyze Compression command. It's built in to Redshift. Now, I said almost always. Now, there are cases where you'll notice that analyze compression will return back an encoding type that called raw, which means basically no compression. And it'll do that for small tables or sparse columns, basically columns that are filled pretty much with nothing but nulls. So the next piece of terminology to introduce you to is blocks. Blocks, they were represented in the previous slides by those kind of orange squares there. It's basically what the data is stored in. And in Redshift, we use very large 1 meg immutable blocks, which means we never change an existing block. We always write only new blocks. And the blocks are encoded with one of 11 different encodings, which, like I said before, is interchangeably used with compression. So one of those encoding types is raw, which means uncompressed. Now, when you factor compression in and the fact that they are 1 meg blocks, we typically see hundreds of thousands of records in a single block. And sometimes if the data compresses very well, even up into the millions of rows in a single block. So the next piece of terminology is something that we call zone maps, which are really just metadata about the blocks. And the important piece of information, or that metadata, is that we store the minimum and the maximum value for each of our data blocks. This allows us to prune data out at query time. So before we read a block off disk, if we say know what value we're looking for in that block, we can look at the zone maps and decide whether or not it makes sense to read that block. And the whole goal of this is to further reduce I/O. The next piece of terminology is something we call it's data sorting, which is really just the physical sorting of one of our tables. And the goal or reason we want to do this is to make the zone maps more effective. Because if we sort the data in the blocks, it'll make the pruning much more effective. And we can only obviously pick one way to sort a table. So picking the sort key, as we call it, it's usually based on your query patterns in most cases. Obviously, there's some business requirements, and maybe even the cardinality of your data is going to play into picking the correct sort key. A sort key can span more than one column, so you can pick multiple columns when picking the sort key. Just as an example of how sorting works, this is the same table I've been using in the earlier examples. Let's just say, we wanted to add a sort key to this table. We can modify the DDL up there, again in the red, and in this case, I've added a sort key to both to the date and the location column. So we're going to sort first by date and then by location. And if we were to take this table and sort it, obviously the first date here is going to come up and then the second date. And then here we have two dates that are exactly the same. So we're now going to look at the location column to pick the order for this. And then the next record, and we have our fully sorted table. And that's how the data would look if you added a sort key to this table. So combining sort keys and zone maps, which I mentioned earlier, that's the reason why we want to sort data. Let's just, suppose we have our unsorted table here with some dates in it. And you can see the zone maps printed out there, which are the min and the max values. If we were to come along and write a SQL query, we just want to count the number of records on a particular day, what would happen is we would check the zone maps first, and we would determine which blocks we need to read off disk. So in this case, we know we can prune out this one block here, and we've reduced I/O. Now, if we sorted this same table by the date, what would end up happening is we would have zone maps that went completely in sequential order, like this, and we know exactly that we only need to read just this one block off disk, and we've effectively pruned out more data and decreased I/O. So the best practices for picking a sort key, typically in most data warehouses, it's going to end up being some sort of temporal column on your fact tables, and that's because in most fact tables, it's, this is time series data usually. And so it usually makes sense to have that as your primary column so that we can effectively just query the range of dates that your, whatever your SQL query predicate is on or querying. The next is, and this is kind of more of a design consideration, if you end up having a high cardinality column, it doesn't make sense to add additional columns after that. It would actually make more sense to reverse the order of the sort key in that particular case. And that's because if, say, you had a timestamp that had granularity or all the way down to, say, milliseconds, for example, it doesn't, after that value, you're not going to have any value in sorting the second column. So it would make sense in that case to change the order. As a general rule of thumb, usually it also doesn't make sense to have more than 4 columns in a sort key. In fact, usually in most cases, most customers usually only use 2 or 3 columns typically. And it's just because there's just marginal gains after that, and there is some extra ingestion overhead when you're ingesting and needing to sort that data. I'm also going to call out that we have some links here on GitHub that you can use. These are some scripts that we've written and put up on GitHub that can also help you determine which columns that you typically filter on to determine the sort key. So if, again, you're still unsure, maybe you don't have a good temporal column to make your primary column of your sort key, you can check, run those scripts there, and that might give you some guidance. This next piece of terminology is very important. It's what we call slices. And what slices are, they're basically like virtual compute nodes. And it's how we get parallelism within each one of our individual Redshift clusters. So all of the data that you store in Redshift is written to a particular slice. Then each slice has associated with it a set of compute processes, and those will only operate on the data that belongs to it. So that leads into how do we get data to these individual slices, or how do we determine how the data is distributed? Well, here we have 3 different techniques for distributing data in Redshift. The first I'm going to talk about is even, which is really, that's just the default choice, and it's just round robins the data through the cluster. So you send data, and we just evenly spread the data across all the slices for you on your behalf. The next choice that you have is where you pick a column to be the distribution key. And what we essentially do is we take the value for that row on that column, we hash it, and that hash corresponds to one of the slices in the cluster. And this is typically done to improve performance between 2 tables when you're joining them. So that's the typical reason why you're going to pick a distribution key. Our last choice of distribution is kind of a special case one. It's for small tables and optimizing join performance with small tables, and actually even also the storage. And what we do in that particular case is we make a complete copy of that table on each node in the cluster. So not on a slice, but for the node. I'm going to go on and illustrate how these different distributions work. This is the same table I've been talking about, same 4 rows. And underneath this data here, I've represented 2 of our compute nodes, which have 2 slices each. So this is a very small cluster that has a total of 4 slices. And if I were to distribute these 4 rows evenly throughout the cluster, what would happen is this first row is going to land on our slice 0, and the second row is going to land on slice 1, and so on, until all 4 of those rows are evenly distributed throughout the cluster. Now in this second example, I'm going to pick a distribution key. In this case, it's going to be, I'm going to pick the location column here. And the data represented in this, this data is going to be this SFO, JFK, SFO, and JFK. Those are the values associated with the location. So we'll pretend we look at this and we see, okay, SFO happens to hash to slice 0. JFK, we'll say, happens to hash to slice 1. SFO is going to end up going back to slice 0, and JFK is going to end up going to slice 1. Now, in this particular case, what's happened is we have no data on our second node in the cluster. So if you were to execute a query against this, one of the nodes in the cluster does absolutely no work. And this is actually an example of a bad distribution. It's what we call row skew in this particular case. So I'm going to pick a better key here. So in this particular case, I'm now going to pick the audience ID here. And this looks like a primary key, so it's a high cardinality column, lots of unique values, and we're going to go with this one instead. And in this particular case, that first row ends up now hashing over to this slice, and the second row over to slice 2, and the third slice over to slice 0, and so on. And I've obviously made the example work perfect, but statistically over a large quantity of data, you're going to end up with a nice even distribution of data if you pick a high cardinality column. And the idea here is to make sure the data gets evenly spread throughout the cluster. Now, distribution style all. What this distribution style does is, like I said, we store one copy of the data on each node. And how we do that is we write each row to the first slice on each of the nodes. So we end up with a complete copy, all 4 rows on the first slice of each node. So the best practices for data distribution, the most important piece is that if we're going to pick a key, that it doesn't cause any skew. Now I have a SQL query here up on the screen there, which queries are svv_table_info table. And within that table, there's a column called skew rows. And ideally, you want that column, or the value in that column, to be as close to 1 as possible. What that value represents is if we were to take the slice with the most amount of data and the slice with the least amount of data, it's the ratio between those two. So like I mentioned before, the reason to pick a distribution key is to optimize joins between large tables. So this would be picking the column that you use in your on clause in the SQL join. It can also optimize performance if you're doing insert into with a select statement from another table. If those 2 tables share the same distribution key, you're also going to get better performance on moving data from one table to another. If distribution style key doesn't apply, maybe there's it's too big of a table, or sorry, it's maybe there's just no good column to pick. What you're going to want to end up doing is you're not going to want to pick distribution style key. You're going to want to pick one of the other 2. If the table happens to be small, that will be distribution style all. And we define a small table as being under 3 million rows. So if you have a small table that you're typically joining to, these are usually dimension tables, then you'll want to pick distribution style all. If the 2 above, distribution style key and all, don't apply, then you'll want to pick distribution style even, which is the default choice. So just to summarize, and actually also add a few extra points, one thing that we've noticed is in Redshift that you'll want to avoid distribution on temporal columns. It usually doesn't work out very well to pick, like say, a date, for example, to be the distribution key. The next is to make sure you are always adding compression to your tables. We talked about that, so I'm not going to cover that too much more. And obviously to add sort keys to the columns that you primarily filter on. Now, just to add a few extra points that weren't covered earlier, so it's kind of more than just a summary, is if you have columns in Redshift that you're typically having to do calculations on, maybe you're having to add 2 numbers together and you're filtering on that, it makes sense to just simply write out that extra column in Redshift and do the calculations in advance and write it out. It also makes sense if, say, you have dimension tables and you're frequently filtering on the values in those dimension tables. So this might be, say, like a time dimension table, for example. it makes sense to move that data or those columns into your fact table. Even though it's going to cause some extra duplication of data, it makes executing queries against that table much faster. And that's because it allows you to leverage the zone maps that we talked about earlier. One last point I'll just bring up is that varchars and chars and numerics, ideally you want to keep those as narrow as they kind of need to be. And that would be like, if you say, for example, you were wanting to store some sort of, maybe an abbreviation that's a couple characters long. You're not going to want to make that a varchar 255. You'd make it, say maybe a varchar 10 or something like that. And while Redshift will store data as efficiently as possible, or it'll be just as efficient either way, it does take up a bit more memory at query time if they're longer than they need to be. So you don't need to go, completely, trying to shrink everything down as much as possible, but just, within reason. So let's talk about data storage in ELT. So just to build up, obviously Redshift has disks. It's backed by EC2. The data storage that we advertise on the Redshift pricing, the Redshift nodes actually have 2.5 to 3 times more storage than we advertise. And the reason we do that is we mirror data within the Redshift cluster. So each compute node mirrors its data to another compute node. Then there's also, an operating system, and we have space reserved for, spilling to disk and things like that as well. So essentially the size of the nodes that we advertise is the amount of space you get to store your data. We talked a little bit about how we mirror the data from one node to another. The one thing that this kind of ties into is that means commits in Redshift they're a little bit more expensive, obviously. This is a 2-phase commit in that we have to write data to 2 different tables or to 2 different nodes. The other thing that we also do is we also asynchronously back up the data to S3 as well. How we do that is, or determine that, is every 5 gigs of change data, or 8 hours, whichever happens first, we synchronize and flush all of the data in the nodes to S3. You also have the option to take a manual snapshot at a time, so if you say I want to create a save point, you can also do that. The exception in this is temporary tables. Temporary tables don't write out a mirrored copy and they don't back up, which kind of makes sense because they are temporary. That has a benefit, though, that they do, that is they write about twice as fast as a permanent table. In certain cases, particularly with staging tables, it can also sometimes make sense to declare a staging table without the backup no option on. And that means that table won't be backed up to S3, so that it won't trigger that 5 gigs of change data. Now, Redshift is an ACID-compliant data warehouse. It supports full transactions, like I mentioned on the previous slide. It also does, we do 2-phase commits within Redshift. So the design consideration here is that to keep commits to a minimum. Redshift can handle a fairly reasonable rate of commits, but what a lot of customers don't realize will sometimes happen is when they're issuing DDL statements one after another, that each one of those causes a commit. So in certain cases, it really makes sense to help improve performance to batch those up within a transaction. So if you have an ETL workflow, you're probably going to want to have it wrapped up into a transaction with a begin and a commit. The next is our copy statement. This is the typical way that most customers ingest data into Redshift. In this particular example that I have here up on the screen, I have one of our DC2 8XL nodes, which has 16 slices. And I have a single file, we'll say is on S3 here. And if we were to run our copy statement and say, hey, Redshift, please copy this file off of S3 and into the compute node, what's going to happen is one of the slices in the cluster is going to reach out to S3, pull that file up into the cluster,
It's obviously going to parse it. It's going to distribute it to the other slices depending on your distribution style, and it's going to get written out. Now, in this particular cluster, if I were to split this file up into 16 even pieces, because this cluster has 16 slices, what's going to end up happening is every one of those slices can now reach out to S3 in parallel, pull the file up, they can all parse it, distribute it, and all write it together. And by doing this, we actually get linear scaling in Redshift. So this would run roughly 16 times faster than the previous example. Our best practices for splitting these files and sizing them is to have these files somewhere between 1 meg and 1 gig after gzip compression. Ideally, there should be an equal number of files as there is slices, or a multiple of the number of files to slices. So for example, you could have 32 files, and that would work just as well. Some best practices I've kind of run into while working with customers is, we support a various file formats for ingestion. If you're with a copy statement, in most cases it makes sense to use a CSV file. And using a CSV file, pick a simple delimiter, pipes, tabs, make sure you wrap things in proper quotes, pick a simple null character, make sure obviously you escape things like double quotes and things like that as well. One other note they'll make note of is that UTF-8 characters, if you're storing those, they actually take up 4 bytes per character in Redshift. And when you declare a varchar column in Redshift, the length is actually bytes, not the length of characters. The next is Amazon Redshift Spectrum. Ingestion with that. So I mentioned earlier that you can load data through this, or through Spectrum. And what happens with Spectrum is the Spectrum, or the data in S3, is exposed to Redshift as an external table. And Spectrum, obviously you'd be running SQL queries against this, but you can run an insert into a table in Redshift with a select clause. So this can allow you to do aggregates while you're moving the data off of S3. You can potentially filter data, select a subset of columns, and essentially manipulate the data in any way that you can with SQL. The other advantage of this is it also pushes the compute that would be normally done in your Redshift cluster down into this elastic Spectrum layer, which reduces the amount of ETL or ELT load on your cluster, and obviously saves your cluster's resources for things like reporting and dashboards and things like that, which are probably more important to you than just the ingestion of data. Spectrum, how we charge for that, there is an additional charge. I'll call out, it's $5 per terabyte of compressed data scanned. So it's a very low cost. It's the same cost actually as Athena as well. One design consideration with Redshift when you're ingesting data is that Redshift really is designed around batch processing, so moving very large amounts of data. And remember when I was talking about the block sizes and how you can, each block can store hundreds of thousands of records? That means that the overhead to write, say, just a handful of records, 1 record, 2 records, 10 records, is roughly the same as writing, a couple 100,000 records of data. And again, that's because Redshift really is designed around big data. Updates and deletes in Redshift. Deletes, we just tag the row as deleted. That's for Redshift supports what's called multi-version concurrency control. That allows that so transactions can read deleted data if their transaction's long running and they need to. With an update statement, what we end up doing is we end up just tagging the row as deleted and we reinsert it to the end of the table. So an update is really just a delete and an insert in Redshift. And then I'll talk a little bit about vacuum and how we clean up the deleted rows in a few more slides. So this is one of the most commonly asked questions that I get in Redshift is, how do you do deduplication or UPSERT logic with, say, the copy statement? Say if I have the data in this deep dive table, the same 4 rows we've been using this entire webinar, and we came along with a CSV file. And in this CSV file, we have another 4 records. And we want to update 2 of the records, and 2 of the records will result in new rows in the table. How do we go about doing this? The steps to doing is we're first going to create a staging table and load that CSV data into the staging table. Then what we're going to want to do is we're going to want to delete the data out of our production deep dive table where the records match, and then we're going to insert all of the records from the staging table into the production table. The SQL for doing this, we're going to want to start out with a transaction. Remember I talked about transactions in Redshift and how we want to wrap these workflows in a transaction to reduce the number of commits. So we're going to start out with a begin statement. Then we're going to create a temporary table because temporary tables write twice as fast. We're going to create this temporary table just like our deep dive table. So it's going to copy over all of the compression settings, the same sort key, all of that stuff from that table. We're then going to copy the data from S3 into our staging table. And now we can delete the data out of the deep dive table where the records match, and then insert all of the data into the deep dive table from our staging table. We can now safely drop the staging table and finish the transaction with a commit. So all of this happens in a single transaction, and it all happens or it all rolls back. So that is the optimal way to do deduplication UPSERT logic in Redshift. So just to kind of cover over, summarize our best practices, like I mentioned, make sure everything's wrapped in explicit transaction. Consider using drop table or truncates instead of deletes. They don't result in any need to vacuum or clean up deleted records. If you're going to be using staging tables, which are very commonly used, consider using a temporary table if your workflow supports it. If it doesn't, consider using the backup no option so there's less backups running in the background to S3. If possible, make sure that the 2 tables, your staging and your production table, also have the same distribution key so that when you execute that insert into select, it's going to move data quicker. The other thing is, remember how I mentioned that Redshift tries its best to figure out the optimal compression the first time you load data into the table? Ideally, you'll want to basically use that create table like statement so that the table already has compression set, so Redshift doesn't have to figure out the optimal compression for that table. Now onto vacuum and analyze. Vacuum is used for removing the deleted records. So those ghosted records that were deleted, this process will clean those records out. It will also globally sort a table. Every time you load data into a Redshift table, Redshift will do a sort, a local sort we call it, but the table eventually does need to be globally sorted. So vacuum does both the removing of the deleted data and the global sort step. Most customers schedule this to run once a night, once a week, somewhere around in there, depending on how often, how much deleted data you have and how often you're deleting data. The other kind of maintenance task that's left onto you to schedule is analyze, and that's really just to gather statistics from the table to help the query planner pick optimal plans. We have a utility here on GitHub, this link here at the bottom of the screen. A lot of customers, they'll just download this utility. It's a small Python utility, and they'll set it up to run through cron or something like that to vacuum and analyze the tables on a schedule that works based on your business requirements or when you have idle time on the cluster. So moving on to workload management and query monitoring rules. Workload management is really meant to allow for you to separate different query workloads. This is to prioritize one workload over another. So a lot of times you'll have your ingestion, you might have dashboards that are running, and maybe some data science users that are executing queries, doing analysis, and this allows you to give priority to one of those workloads over another. So to build up some of the terminology around this, the first is what we call queues. Every SQL query that's executed in Redshift will run within one of our queues. The queues, what determines what queue that query runs in is based off of the group that the user executing the query belongs to. The next is you can also manually set a session variable, and that will force the query to execute within that queue. Now the next piece of terminology is what we call slots. Each one of our queues are divided up into a number of slots, and this is really the division of memory within that queue. So a query needs one, or in certain cases more than one slot to execute, and that's how you're able to divide up the memory. So just to come up with an example or kind of build up for best practices of how most customers or many customers set up their WLM, I just came up with this example here. It's, maybe you have some light ingestion that continues to run throughout the day. Then then you have, your peak querying, reporting, dashboards and such that run, through business hours, 7 a.m., 7 p.m. After that, you have in the evening ingestion, that heavy ingestion where you're pulling data from all these different source systems and getting that data into Redshift through the night. Handful of different users, analysts, DBAs, business reporting users, and dashboards. So a handful of different users and user types. How I would recommend setting up a WLM configuration for kind of that example is having a single queue for ingestion, and maybe setting 20% of memory to that queue, and having 2 slots. What that means is that each of the queries that are going to be loading data in this example would get 10% of the cluster's memory. On the next queue there, I've set up a queue for dashboard queries. So these are really short, fast, zippy queries, ideally, running in the order of seconds, hopefully, under a minute or two, basically. And I've put a timeout on this queue of 2 minutes, just as an example. And each one of these queries will get 5% of the cluster's memory. Now, the last queue here, which is the default queue, so if none of the either 2 queues match for that user, it'll run in this queue. I've assigned 8%, roughly a little over 8% of memory to each of the slots or queries that execute in this queue as well. Now, we also added somewhat recently something we call short query acceleration. And what short query acceleration is it's where Redshift determines if a query is going to be quick or short running, maybe running on the order of a few seconds. And what would happen is if, say, for example, you had some analysts that were running queries and, we can only run 3 of them concurrently, and so a 4th analyst comes along and executes a query that's going to run in a couple seconds. Redshift will actually run that query immediately just to get it out of the way, and there won't be any queuing if you have this short query acceleration flag turned on. And it is quite literally just a checkbox in the console to enable that feature. If you've done the math and you notice that you added up the amount of memory I've assigned to each of the queues, it equals 95%. That's because if you leave unallocated memory, I did that on purpose. For this reason. If you have unallocated memory, it's used by any queue on a first come, first served basis, and then added back to kind of that general pool. The other thing to make note of is in the console, it's not visible. It's in the documentation and everything. There is also a hidden super user queue that you can use for the DBAs and such that all super users can switch to. So that can be used for administrative tasks. The next is QMR. This is really just an extension to WLM, and it really is meant for, or is originally meant for runaway queries, basically poorly written queries. You have analysts that connect, write Cartesian products, return billions of rows, basically running wasteful queries. And it allows you to programmatically detect and kill those queries. As an example here, metrics, we have a whole bunch of different metrics that you can check for and write rules for. So for example, maybe you want to have one where, return 10 million rows or more. You can set in the rule to abort that query. Maybe you don't want to be aborting queries. You can also just simply log the query as well. So as a general rule of thumb, when setting up WLM, I typically recommend only keeping the WLM queues to a minimum, usually 3 or less. Some customers will run with 4. And this is to avoid having unused queues. A lot of times, if they get into these elaborate WLM setups, a lot of the queues sometimes will go unused. And most customers really usually only use about 2 or 3 queues and actually fill those up. The next is to keep the total number of concurrent queries across all those queues to 15 or less. And the reason to do that is because that's where we find you'll get optimal performance in Redshift. You can set it higher, but if you do that, the total throughput in the system can drop. The other thing is SQA can only be enabled when it is 15 or less as well. So in most cases, you'll find you'll get optimal throughput, again, setting it to 15 with SQA enabled. Now, moving into node types, cluster sizing, there's really only 2 choices here. We have our dense compute, which is basically solid state, and our magnetic disk, which is dense storage nodes, the DS2s. The difference between them, obviously the SSDs are faster, however, they do cost more. And so picking the node type is, again, based on your business requirements. Are you more query-bound, compute-bound, or do you have a really large tail of data and you're storage-bound? So there's the 2 different, picking those there's pros and cons to that. Now, that being said, a lot of customers recently, since we've released Spectrum, use dense compute and offload the longer tail of data to S3, where it then remains queryable, and using S3 essentially as a form of tiered storage coupled with Redshift Spectrum. So the best practices on cluster sizing really is about sizing your cluster, picking the node type first that you know you want to go with, dense storage or dense compute, and sizing it first based off of the amount of storage that you need. So for example, if you had 10 terabytes of raw storage and you assume roughly 3 terabytes after compression, you would need probably close to about 5 terabytes of space to maintain a healthy free space amount. Our rule of thumb is that ideally it should be somewhere between around 30-ish% free space. Once you start hitting upwards of only 20% free space, you really should be thinking about resizing the cluster. The reason why is vacuum, some temp tables, things like that require free space in the cluster, and you just have to have that kind of buffer room to really kind of do proper vacuums and create temp tables and things like that. There probably isn't very many of you out there running EC2 Classic, but if there is anyone out there listening to this that is running EC2 Classic, please switch to a VPC. Typically, customers see somewhere in the neighborhood of a 2x performance increase by switching from EC2 Classic to VPC, and there is no cost in making that switch. The other thing is if you also have DC1 instances, you can move those to DC2, and we will even convert your reserved instances over from DC1 to DC2, and DC2 is significantly faster than the DC2 is significantly faster than DC1. So just to quickly go over the additional resources, the whole webinar has been littered with these GitHub links. We have the Amazon Redshift utilities. That's where most of these links are. A lot of great resources there. I've been talking about, like I said, the vacuum utility is very valuable. Lastly, we have a handful of blogs that are worth checking out. This top one is a design playbook. It's a series of blogs that's very good. It covers a ton of these different patterns. And then another one, both for Spectrum and for Redshift, which are kind of the top 10 things that we see in the field that we have put up on there if you're wanting to tune your Redshift cluster. Thank you guys very much for the webinar today, and we will take questions with whatever time we have left.